either take down through the sewer or back by a truck that picked it up the fluid that was left over, whatever that turned out to be, whether it was a hydroxide or an acid.
Do you think Tesla was a few steps ahead of that with his wireless electricity? Wireless
hoped to do it with harnessing the fields of the earth. The idea was that, as Tesla realized, you could get an electric motor or a generator to operate through a distance without contact. You could get electromagnetic field to operate through a distance without contact. So he envisioned using the Earth's electromagnetic field for the purpose. The problem with exercising that type of current development is that it takes a very large apparatus. We've tried to do it with some space flight where there was very little drag, but that has not succeeded.
I turned on a Tesla coil. We got a Tesla coil about 5 feet tall once. I turned it on in a room back in the 80s. And he erased every floppy diskette in the room. The room was 8 times larger than this place.
Yeah.
Every floppy diskette.
Theoretically, they run into another big problem, though. They couldn't figure out how to charge for it.
That's true. Well, it is a... Well, the reason that Edison didn't get the plates in because it looked like to his stockholders that had the same problem. Somebody else would be delivering them. I mean, their main concern was, well, that's just going to invite every competitor that couldn't get there with another delivery to take our place. I just have to inquire, does Dell need some help? No. Okay, well, we're right on schedule. Please.
Could you talk briefly about low pressure hydrogen storage tanks?
If you want to go low pressure, you almost immediately require hydride storage or cryogenic storage. You can go ambient pressure with cryogenic and have very dense hydrogen. Or you can go pretty dense with hydrides. And the hydrides can store actually more hydrogen per cubic measure than liquid hydrogen. The problem is you have a big tear weight in the hydride that you use for the storage medium.
But if you're staying stationary,
It doesn't matter.
But that's true.
what's the hydride material typically made of? The absorption?
Well, it can be a lot of things. Almost all of the metals form hydrides. And some of the metals form hydrides that are easily recycled, or cycled, I should say, in which they take up hydrogen, give off heat. Then you keep them away from heat until you desire the hydrogen, give them back the heat, and they release the hydrogen.
Such as nickel, probably one of the ones.
Well, such as iron, titanium, copper alloys. Iron, titanium, copper form readily cycled hydride systems. And they do so because the titanium presence forms a surface, or provides a surface that dissociates diatomic hydrogen into atomic hydrogen so that it can readily enter the lattice of the alloy and stay stored until you want to give back heat and release it. But others are sodium, lithium, magnesium, calcium, make great hydrides.
Sodium.
Sodium.
How about carbon whispers?
Carbon is going to store hydrogen in the future very densely. There are some special structures that are high surface to volume structures, such as whiskers that are made of scroll type section that have a lot of surface to volume and have a capillary effect for storage, which gives very dense storage.
There was an article in the Hydrogen Fuel Letter, I guess, a couple months ago that talked about a couple in Boston that claimed they could get 5,000 miles of hydrogen storage in a carbon whiskey hydride.
We haven't been able to verify that reference. We've had discussions with them. The numbers that they gave us didn't produce that density. But they are doing something very exciting. They're making very high surface to volume ratio material, which is very conducive to storage. And they're making the spacing conducive for capillary addition and release, which is good.
That would be a low pressure type of storage.
It can be low or high. You can use it in both low, medium, and high pressure regimes. But yes, it'll store a lot of hydrogen at low pressure, some more hydrogen by adding pressure. But the bulk of the storage is by surface arrestment of the hydrogen motion, which gives the advantage of being low pressure.
So is there any kind of a hydrogen storage system you can build for a few $100s?
Yes, absolutely.
What would that look like and how would we do it?
How much do you want to store? It begs 21 questions. Let me go through some of the questions that you need to answer. You need to answer the design questions of how much tare weight is tolerable in your application. How much weight do you have as dead weight in your application? You need to answer the design question of how are you going to load and unload. If it's a hydride, you need to remove heat on loading, add heat on unloading, for instance. You need to answer the question of what does it do to your duty cycle to carry dead weight? Does it wear your tires out or wear your brakes out or whatever? And do you have to add capacity to your existing running gear? Do you have to put on bigger tires and bigger wheels and bigger shocks and bigger springs and
I don't think we're talking
what
about
have you?
mobile application.
Right, just a stationary application.
I see. Well,
Demonstration purposes.
well, compressed can't be beat.
Okay.
Cheap storage is to adapt a scuba tank.
Scuba tank.
And we have contacted the manufacturers of scuba tanks, and in most cases they have been willing to let us re-rate their tank from air storage to hydrogen storage.
And how do you do that?
Well, you just pick one that we've already had it re-rated, so you don't have to do anything.
Find
But
when
if,
it fails.
say,
You're finding out when it fails.
well, that's right. We do safety tests on it.
So
And then-
we, like, buy those tanks from you, is that what you would do?
We could do that, sure.
Okay.
But the idea in that regard is that there's a relatively high volume manufacturing already behind their product.
Right.
So they've already ironed out the cost of tooling and whatnot. The incremental price is what you want to enjoy. Producing one more tank for you out of their assembly line is really easy. What you don't want to do is to go to a one-up type of design that's new and hasn't been proven and has to go through all the testing.
Right. Exactly.
So scuba in small storage,
AHA ought to have a catalog then. of
Well,
specific
probably right.
parts that we could order.
well, we do of sorts in the back of your blue book.
Right?
Yeah. But I would emphasize, if you want to go up in storage from that, you can go to any of a number of seamless tank manufacturers that make tanks for the technical gas delivery industry or technical gas manufacturing and delivery industry. Taylor Wharton and others. If you want to go larger than that, then you go to one of the companies that manufacture tube trucks. Tube trucks are on the road carrying technical gases, and you order one more tube out of the tube truck factory, or the tube factory for the tube trucks. If you want to go larger than that, you still stay with that same manufacturer because they probably have the ability to put in larger diameter tube development for you. If you want to go larger than that, go liquid. Or go precursor, such as take ammonia and convert it to hydrogen as you need it.
How would you do that?
Oh, just run ammonia across the catalyst. It'll release hydrogen. You can do it any of a number of ways, but that's another way is to store the precursor
And hydrogen ammonia.
and hydrous. If you want to go larger than that, buy a depleted gas well and load it with hydrogen. Seriously. That's cheap storage.
Figure out how long it takes you to fill that up.
Yeah.
The government to
At a half
will you one of these strategic reserves.
Right.
They probably
They got some. They got a lot. Yeah, unfortunately. We've been,
Burn it up in 10 seconds.
I hadn't thought about ammonia.
Yeah.
That is. Oh, shoot, I hadn't even thought about that.
and that's common. That's a common ingredient.
That's byproduct of manure.
Some of the lunch you had was by electrolysis hydrogen source, and some of it was by dissociation source. But you couldn't tell the difference. I mean, it was all okay with you.
What would be the energy equivalent of ammonia and hydrogen ammonia?
Oh, once you take the hydrogen across the...
I mean, per gallon.
Oh, well, I'll tell you pretty soon. I'll look it up.
Per pound of anhydrous would give you how many pounds of, or how many pounds of anhydrous ammonia would it take to get a pound of hydrogen?
Well, here's you can do it yourself. You can just look at it. Well, just look at ammonia. It's 14 plus 3. It's 17. It'll be, the molecule will be 17 grams or pounds, however you would choose to do it. And it'll be 3 out of 17 hydrogen units.
Wouldn't be that much.
Well, it's not so bad. That's close. Look at methane. Methane is CH4, so that's 1216. 12 with the carbon, 4 with the hydrogen. So you have 4 out of 16 units, weight units, out of methane. You'd have 3 out of 17 with ammonia.
Would be wasted, that's right.
But that is not a bad tare weight, incidentally, because that's a lot of hydrogen yield for the occasion.
It's about 18%.
And it's easier to extract it out of ammonia than it is from, say, natural gas.
Oh, it is. Yes, it is. And you wouldn't have any carbon, anything, in your catalyst threatening
What would you
chemicals.
have if you were wasting there?
Nitrogen. This isn't so bad. If your system tolerates air, it probably will tolerate the byproduct.
Ammonia is in gaseous form in large.
No, you'd buy it as liquid probably. You'd keep it under 100 psi and
Oh, yeah,
carry it.
you
But the thing
couldn't
is-
get enough volume for finding gas. It
Thing
stays
is-
under liquid really
The
good.
thing is, you're better off producing ammonia from hydrogen production.
Yeah, you can.
Ammonia is expensive. It's a high dollar value product.
Oh, pretty high, but you could.
It's highly produced, largely produced. It's fairly reasonable.
Let's go through that. If we had to start from scratch, if we didn't have the fossil gift, ammonia would be important as a hydrogen carrier, more important than would methane. Here's why. In the atmosphere we happen to have, it's about 80% nitrogen. It's only 3 in 10,000 carbon dioxide, which is easier to get. Boy, that nitrogen comes way ahead. It's easy. And in terms of energetics, you can run the ammonia, the nitrogen fixing at a high production rate with straightforward catalysts and pressure.
What kind of catalyst would you use?
Well, it depends on the regime you decided to run, but there are ready-made hot and cold running catalysts. And there are several process flow sheets that you can go on.
But they still take it out of natural gas.
It's a strange world we live in. Yeah, it's a strange world we live in.
Well, they make it out of
Almost
natural
all the production comes out of natural gas.
gas. Okay, go ahead.
There's a really important comment that I'd like to make with respect to storage. The right storage isn't a universal. There's no one system that is the right storage. What you want to do is custom apply storage technologies to your application. You really want to fit the storage that fits, that suits your application, and not be deterred by ours is best type advertising. What you want to do is find the right size storage for the application, the right tare weight for the application, the right chemical nature for the application. So there's many, many ways to store hydrogen. One good way for some applications is to carry water and release hydrogen from water by electrolysis or otherwise. You know, you might look at a trip to the desert and say, well, which would I rather carry, a photovoltaic panel, illustratively, or some sodium? The photovoltaic panel will give you a lot of other benefits. You can use it to run your toaster and what have you. Shave. You can use it to read at night. You can store up some energy and use that as a primary source of energy conversion. Anyway, you have to make those considerations. Another good way, of course, as we've discussed, is to carry it in a compound such as methane or propane or gasoline or mothballs or whatnot, and then release it on demand. Another good way is to carry it as compressed gas. Another good way is to carry it as a hydride. And among the hydrides, you may have use for the metal that is forming the hydride, or the non-metal that's forming the hydride. For instance, you may take sodium hydride and use the sodium hydroxide that's left over for processing food. It has a lot of applications. Or you might take potassium hydride and use it as a supplemental mineral to your nutrient value, to your food intake. And same with calcium. You could take calcium hydride and still eat the leftovers. You could figure out how to make it a compatible source for long-term planning for your nutrition. Liquid hydrogen has a great application as being a heat sink. If you want to use the latent heat of evaporation, it's a excellent constant temperature reference, but it's also very cold even at that vaporization temperature. So you have a lot of specific heat that you can dump to it as it comes up to ambient temperature. So among the storage systems, that's kind of a list of things you can do with what's left over. But it's very good to think that whole thing through and not be tattooed with one solution for all occasions. On the topic of fuel cells, the best storage for fuel cells, well, it depends on the type of fuel cell. There are some precursors for hydrogen that are much more adapted to a high temperature fuel cell than they would be for a low temperature fuel cell. High temperature fuel cells can use a lot of carbon. They wouldn't mind it. They can use a lot of nitrogen if you're using a ammonia or ammonium compound to release hydrogen. Or they can run entirely on a carbon or carbon monoxide fuel. They'll also do that for you. Because remember, in most of those high temperature systems, we're diffusing the oxygen towards the fuel. So we're not trying to deal with the chemistry of entering the fuel ion through a electrolyte or a semi-permeable membrane. On the medium temperature cells, the carbonate cells, molten carbonate cells, you also have gained a lot of tolerance to some carbon in your system. Going down in temperature, you still have pretty good tolerance when you get to the 200 degrees C range with a phosphoric acid. They're more tolerant of impurities than the low temperature cells. But when you get to the low temperature cells, you have to start adding catalysts to deal with impurities and surface active agents to deal with impurities. So there are more considerations along the lines of purity when you get colder in temperature. Cells become very simple. They have a number of attributes when they're cooler because we like things that are our temperature. But you still have to incur that question, overcome that question of how do you overcome these side effects of polarization and poisoning of your catalysts. Please.
Could you run steam right into a fuel cell?
Yes, absolutely. You mean for a fuel?
To make electricity, I guess.
Oh.
Steam is, well,
you could run steam with sodium. If you had steam and that was if it was, there are conditions where you do definitely add steam to hydrogen.
Well, you can run steam into a fuel cell if you have an external source giving you the heat energy and steam. We ran into a 1,000-degree fuel cell yesterday.
Sure, and you needed to supply heat to get it. Steam heating is a fast way to bring up, incidentally, a phosphoric acid fuel cell. If you wanted a quick heat up, that's a good way to do it.
what would be the efficiency of that kind of
Well, you still have to expend some fuel. All that does is save fuel and heat up, but then you have to spend the fuel to run it.
You said if you add sodium,
You could,
like these big desert deals they've got out here, the parabolic sun tracking deals, what do they use pure water, distilled water, or is that, could they run salt water through those? If they were stainless steel tubes or, nitro, would that produce sodium steam?
If you heat salt water to drive off the steam, the water part, you get sodium chloride and whatever else was in the seawater.
I understand that, but if you contained it into the steam,
No, it'll precipitate. Those solutes don't want to go away as the water molecule goes away as
stay
steam.
there when the steam came back, building up.
They'd start interfering rather soon and get worse with heat transfer, and you'd have clogging problems. That would be a problem.
Why do you want the sodium in there?
Oh, it was just to think of a way to use the steam if you had it and produce hydrogen by the reaction. You could shift steam to
Not sodium chloride.
sodium hydroxide and release hydrogen.
After it was produced,
That's true. But there are regimes where you'd be interested in doing that. Suppose you were, for instance, producing sodium as a byproduct of some other chemistry, such as chlorine, the chlorine chemistry. You could do that.
the reason I asked, we started using a new steamer. It's called a flash steamer that will steam salt water.
I see.
And we're having some problems with it, but it's real efficient. I mean, you just inject that salt solution into a plane. It's the simplest thing in the world. I guess the salt falls out.
Well, it does. You can,
Clean up. I mean, they've designed it to clean up salt water.
on the topic of steam, sure. On the topic of steam, the fastest steam that you can produce is by burning hydrogen and oxygen. It'll be the fastest, highest quality steam you can produce.
By burning hydrogen and
Oxygen.
oxygen.
It's a fast production. Well,